All right then, so let's begin. Mike, thank you for doing this. I guess we'll start with an introduction of everyone. I'll go first. So I'm Manav. I'm the systems integration lead. I am in charge of training Fran and Spencer. Fran is the deputy chief, or I'll leave the introductions to you. But our starring guest is Mike Fogel. Would you like to introduce yourself?
Sure, thanks, Manav. Mike Fogel, I'm the Payload Engineer on our SPICEsat project, and happy to be here to talk to you all today.
Okay. Fran.
Hi, I'm Francesca. I am the Deputy Chief Engineer for the SPICEsat.
Okay. Good. And Spencer.
I'm Spencer, and I'm the Deputy Systems Integration Lead for SPICEsat.
All right, sounds good. So let's begin. So the first question, Mike, what is our mission? What is your research?
Thanks, Manav. So the mission, the project is called SPICEsat. SPICEsat is an abbreviation or an acronym for Sloshing Platform Sloshing Platform
In orbit.
In-Orbit Controller Experiment, or SPICE, Sloshing Platform for In-Orbit Controller Experiment. So what our mission here is essentially to launch a 6U CubeSat into orbit with a tank inside of it with a propellant type analogy, probably distilled water, excite sloshing in that tank, and measure it with 3 different measurement techniques. Use that information, beam it to the ground, and then see if we can mitigate the effect of that sloshing on the rest of the satellite itself. So that is our mission. My research thus far to date has been focused largely on doing that through simulations using various nonlinear dynamic equations to attempt to replicate what that sloshing would be using what are known as equivalent mechanical models, essentially simulations amounting to either a pendulum type model or a multiple spring mass type model, which simulates the sloshing, generates the disturbances from a sloshing effect in a satellite, and then mitigates for it. And the work I've done to date has been focused on control algorithms using machine learning. And so at least in simulations, we've been able to prove that if you can predict the sloshing, then you can compensate for that disturbance through an active control mechanism. So that's what we want to test in SPICEsat.
All right, sounds good. So that is that is a great overview. I guess the first question is, what factors affect the sloshing disturbance, and how is this relevant to actual space missions besides our own?
Sure, it's a good question. So, I mean, there's a number of factors that affect sloshing in a satellite. One of them is the fill ratio. That's the amount of propellant that's left in an orbiting satellite versus the mass of the satellite. So if you have a large satellite with not a lot of propellant, the disturbance is not going to be that significant. If you have a small satellite with a lot of propellant, then when you maneuver, that sloshing can have a quite considerable effect. Another thing that affects sloshing in a satellite is the angular acceleration, or the speed in which you change the orientation or attitude. It's called attitude in a spacecraft. When you change the attitude of the spacecraft, if you do it slowly, you'll disturb the propellant a lot less. If you do it quickly, then your angular acceleration is higher, so you'll generate a larger disturbance torque. Another effect that can change the sloshing in a propellant tank is the properties of the propellant itself, the density and the surface tension of that propellant. Typically, you're looking at things like liquid hydrogen and liquid oxygen, of which, in our case, for our satellite, water makes a good analogy for that because of the density and surface tension properties. the tank geometry can make a difference. For the most part, experiments like this are done with ellipsoidal, cylindrical tanks with curved ends. So think of it like sort of an ellipsoid. Um, Many times in actual satellites, baffles are installed. In our experiment, we're not going to go with baffles in our first launch, our first satellite. We may do that in a future one because we want to actually generate sloshing. We want an effect. We want this sloshing effect to be measurable. So we are not installing baffles. But in most satellites today, especially ones that are going to reuse the propellant when they're in orbit, you have baffles, and those baffles act in two ways. They dampen the sloshing mechanically by just being there to prevent it. And it's very similar to what you have in the gas tank of your automobile. There are essentially walls inside the tank with holes in them that reduces the sloshing in the tank. But in the case of satellites that have to be relit while they're in space, they have veins inside the tank, and those veins essentially wick the propellant down to the bottom of the baffle itself to allow the propellant to essentially drain into the pipe so it can exit the tank and go into an engine. So those baffles really serve two purposes. The position of the tank relative to the satellite itself, that is also important. If you have a tank that's in the center or closer to the center, the sloshing effect will be less. So there's a number of factors that kind of determine how bad or how big the disturbance can be.
Right.
And with regard to the fact that this has actually had an effect on various satellites. There's been a few missions. A SpaceX Falcon 1 demo launch in 2007 was affected by sloshing. The near-Earth asteroid rendezvous mission, they actually lost communication with the satellite after a maneuver because of a sloshing effect. Fortunately, the sloshing settled down, and the satellite came back under attitude control, and then they could speak to it again through communication. So this is a real effect.
Yeah,
I have
awesome.
a question there. So I think a concern that UNP has had in the past is that the nature of our experiment is we're trying to maximize the disturbance that sloshing has on our satellite, right? Where do you think like the balancing act comes in where we're trying to maximize the disturbance on our satellite, but that also makes it really hard for us to control our own satellite?
Yeah, that's a good question. I've examined, there's 2 points in which this needs to be examined. I've examined one and can answer that. The one that I can't answer yet, and even UNP couldn't answer, was when this satellite is ejected from whatever launch vehicle, it goes through, it's tumbling, right? So it has to go through a detumble phase, and that in and of itself, coupled with the motion of the propellant, could put us in a situation where it's going to take a lot longer for the propellant to settle. The short answer there is the propellant, the energy imparted into the propellant, it eventually dissipates, right? In real life, you can see it when you look at videos of fluid on YouTube, or even in the simulations I've run. It takes a number of minutes, 10 minutes, 5-10 minutes, depending on how much energy is put into it. It always dissipates. And so detumbling uses magnetorquers that align themselves with the magnetic poles of the Earth to eventually detumble the satellite. So although you can't model detumbling, at least that's what UNP told us, the disturbance is going to lose energy over time, and the magnetorquers will eventually get us to detumble. It may take our satellite longer than a regular satellite without propellant in it, but it will eventually detumble.
Okay, thank you.
But it also important, what I did model was the tank itself. When we do excite it using the reaction wheel, I was able to show through computational fluid dynamics models that we have almost an order of magnitude more control authority in our reaction wheel than we need to compensate for the sloshing under a regular maneuver. So I'm very comfortable with getting the satellite controlled properly under regular maneuvers. We can get sloshing and we can control for it.
Okay.
Yeah, Mike, actually, you jumped ahead a lot, but you're absolutely right with the natural dissipation in that, if we really needed to, we could just let it, rest. We just let it come to rest just by natural, viscous effects. Um, yeah, no, that was a good question. All right, so you've already addressed this, but just to clarify, so what are the main methods that have been used to control slosh in the past, the present, and hopefully the future?
It's an interesting question. And you can look at some really fun videos that exist either at NASA or on YouTube. But early on, this was a consideration for the Apollo program and missions to the moon. The initial methods, they didn't really have a lot of slosh baffling, so they would put these aluminum beer cans, essentially what they were aluminum cans, put inside of the propellant tanks to try to reduce the effect of sloshing. You can see that if you do a search on YouTube. Very, very interesting work. So that's a mechanical way of doing it. Slosh baffles are a mechanical way of controlling sloshing.
Mm-hmm.
But they both have the fact that they bring weight to the spacecraft, right? They bring mass, and that's what you don't want when you put a satellite in space. So others have used active control algorithms, not with machine learning, but some active control algorithms to try to reduce that effect through software, essentially, the way you control the reaction wheel. And that doesn't weigh anything, right? So
Software do be a zero mass solution.
yep.
All right, so let's see. The next one is all right. So you got a little bit into it, in that we do plan on using software. I guess the next question is how is this approach more unique compared to previous attempts? You hinted at it, but just to elaborate on that further.
Yeah, let me know if I'm headed in the right direction. The first thing is the data collection methods. We need to collect data to characterize the sloshing effect so that we can then use novel control algorithms, maybe even machine learning, to predict the sloshing and then compensate for it. So to the question of how is this different, it's different in many ways. We're using 3 different mechanisms to try to capture the effect. One is through sensitive gyroscopes and accelerometers, right?
Mm-hmm.
This has been used before. This was used in an experiment in the early 2000s called SPICEsat. They did a similar thing. We are adding to that a tank that we're going to line with pressure sensors. And the pressure sensors themselves will be inside the tank. They will detect when the water, when the propellant touches the side of the tank. Whenever the propellant impacts the side of the tank, that imparts a torque on the satellite itself. We don't care about the propellant that's floating around inside, but as soon as it bounces off the side of the wall of the tank, we want to be able to detect that with this pressure sensor array and understand what direction the force came in and what the magnitude of the force was. And we're going to do that using pressure sensors.
Mm-hmm.
And then the other novel sensor data collection method we want to use is a video camera. Very simple video camera. We want to see what the fluid is doing. Put it on video. Each frame will have a timestamp to it, and all that data, the accelerometer and gyroscope data, the imagery, and the pressure sensor data, we want to send to the ground, right? Once it's on the ground, we're going to develop essentially a sensor fusion algorithm to try to recover the state vector of what happened during that maneuver that we had, and we'll recover that through using the motion sensing data from the accelerometers and gyroscopes and the pressure sensor data. So then we'll have a picture of what happened over time, and we can use that model, we can use that reconstructed state vector to train a machine learning algorithm. So when the input to the reaction wheel was X, the output was Y. We know what the input is because we're going to tell it to spin at 20 degrees per second. The output was the following effects in the state vector. The torques were this, the pressures were this, so on and so forth. And so we will use that input and output to train a machine learning algorithm. And that machine learning algorithm will then be beamed back up to the satellite, and we will try the same maneuver again and see if we get a reduction in time in terms of how long it takes for the sloshing to settle.
So you said we're going to use the motion sensing data and the pressure sensor data. Are we not going to use any of the video footage, any data we get from that to train the model?
We will. We're still developing what the output will be of the video data. Right now, we're currently working on getting data into a detection algorithm. So we have people in the group working on software. So imagine you have different, essentially a video is a collection of individual still images, right? Let's say 24 frames per second. So we know what the picture looked like at this moment, and then the next moment, and the next moment. We want to take those images, those videos, and run them through image processing software with the intent of detecting two things. One, detecting the outline of our tank, right? We need to know where the outside of the tank is. And two, we want to detect a bubble, because these things in 0G essentially are globules of water. When that globule moving hits the side of the tank, that's going to impart a velocity. So our objective, and we have people working on this software right now, is to detect the size of that globule, which you can measure through image processing techniques, the velocity of that globule, right? If we have successive images and we know where the globule was at this point, and the next frame it was at this point, and the next frame was at this point, we know the velocity it's traveling at. We know the size of it, we know the density because it's water, and then we can detect when it hits the side of the tank. If you put all that together, you can figure out what the momentum was that was imparted between the globule and the side of the tank. So we know what we're doing from an input standpoint. We want to get that far. And then we're going to have to think a little bit more about how we use that data in terms of a control algorithm. But, we're halfway there in terms of where we want to be. Does that make sense?
Awesome. Just to summarize, I think you guys are using a very novel approach by collecting a lot of data, and then being very clever with how you use that data. You guys are going to be able to you guys are going to get more information than you would with any one of these sensors. I believe SPICEsat Clevo had I think sensors on the inside, and then they had accurate accelerometers and gyroscopes. I guess our mission goes a step beyond, and not only the pressure sensors are more up to date, but we also have a camera to get some video data, and we're combining it with the other pieces of data to try to get something extra out of it. And then on top of that, we have the machine learning model, which lots of stuff. Sounds exciting.
Yeah, that's a good description. Thank you.
Mm-hmm. So I guess from here, the next thing we can define is, what would be the requirements for all of these. I guess the main points are, when we characterize the attitude using our motion sensors, what accuracy would you like from there? When we get the pressure on the inner surface of the tank, what would you like? What would you consider as a good enough resolution or a fast enough rate? And then video is video, because all of these do pose challenges to satellites. We cannot have perfect attitude determination. Pressure sensors have noise, and videos are very hefty chunks of data to send down. What would you say is the I guess In 3 levels, what would you say is the most ideal experiment versus what will get the job done?
Okay, that's a good question. These effects are very subtle, so those lines are a little bit blurred here. I can tell you a little bit about the work I've done with regard to computational fluid dynamics, and answer the sensitivity questions that way. The CFD models were conducted using essentially water in a tank the same size that we have, and imparting a maximum angular acceleration on the satellite to match what our attitude, determination, and control system can output. In other words, this ADCS, attitude, determination, and control system, that changes the way the satellite points, that has a maximum speed at which it can spin up our satellite. So I used that information to create an angular acceleration curve, which was then input into the computational fluid dynamics models. And that should be able to, and did, tell me what the pressure sensor sensitivities and what the angular acceleration detection thresholds were to detect the sloshing effect. So far, what I've been able to discern is we need a pretty sensitive angular acceleration, and this is something that we intend on talking more to the UNP folks about, because they have experts that can kind of guide us now that we know what our limits are. We're looking at something in the order of 0.1 to 0.01 degrees per second squared, which is a pretty sensitive measurement. If we are in the lower end of that, that'll be the most ideal. If we are in the upper end of that, then we're only going to detect sloshing in the most extreme torque cases that we can input from the wheel. So I'm really hoping that as we explore our detection methods for the Blue Canyon device that we want to use for an ADCS, that we're in the lower end of that scale. On the pressure sensors, we're in pretty good shape with the ones that we're looking at and other ones in the industry. The pressure sensors are the pressure that I expect to detect inside the tank. You imagine the tank itself, it's going to be sealed on the ground. It'll have 14.7 psi in there. So when the fluid hits the side of the tank and impacts the sensor itself, we're going to be measuring 14.7 psi plus or minus some sensitivity, right? Some effect of the sloshing. So I've characterized that between 0.01 and 1 psi. So that's a range. That's a factor of 100. So we have, and the sensors that we have are capable of measuring that down to even a smaller sensitivity level. So we're in good shape there. We just have to make sure that we get the right sensors put into the tank. But those are the sensitivities we're looking at. One of them we know is achievable, and the other one we have to talk to UNP about.
Just to clarify, you said 0.01 psi up to 0.1 psi?
Up to 1 psi.
Up to 1 psi.
So the full scale range, you had it right on there a second ago. It's 14.71 psi to 15.7 psi.
15.7 psi. Thank you.
Yep.
And so the sensors that we have planned right now, their resolution is on the order of, I believe, 0.008. Or,
that is correct.
Yes,
yep.
0.008 psi is what we as advertised, this is what we expect.
Yes.
All right. And then finally, I guess the video data. What would you say is the frame rate and resolution?
So the sloshing effect, as we all know, is a very slow-moving effect, right? Sloshing in space kind of goes like this, right? It's not vibrating at 100 hertz.
Yep.
So that means we don't need a very high frame rate in terms of the camera. The typical home, when you watch TV, your frame rate is 24 to 30 frames per second, because that's what the human eye can detect. We don't need that because the fluid isn't sloshing around with that effect. So I think we've specified somewhere in the order of 20 frames per second. We can go as low as 10 frames per second. It doesn't matter all that much. The camera itself is going to be flown as a color camera, but we don't need color. We need contrast, which means black and white. So although the camera will capture a color, we're going to instruct it to only record the black and white image. So we have a low frame rate, we have a black and white image, and we're looking for one of the smaller side of resolutions. I think we looked at a 920 by something as a resolution, which is not that big considering TVs today and monitors are much higher. So we're doing this for a handful of reasons, but not the least of which is reduce the amount of data we transmit to the ground.
Yes, that is a concern. 1080p at 60 hertz is a lot of data, very difficult to send. One thing I think may need to be clarified, how long do you expect the experiments to be?
Good question. So we talked earlier about what affects the sloshing. One of those things we talked about was the angular acceleration that you give to the satellite and therefore to the tank. In the cases where I've modeled using equivalent mechanical models, using a rather large input torque, one that matches the top end of the reaction wheel we intend to fly, indicates that the sloshing dissipates 200 to 300 seconds after initiated, right? And this assumes what's known as the bang, stop, bang profile. So you start, you input a torque, you let the satellite move to a certain point, and then you input the opposite of that torque, right? So you essentially give the negative or the mirror image of what you input as a second command signal when you want it to stop. That representation is perfect. That's called the bang, stop, bang profile. If you give it a bang, stop, bang profile, which essentially negates what you inputted after you've turned to a certain angle, 200 to 300 seconds is the answer. It can last longer, up to 500 seconds, but typically with the reaction wheel profiles I've given it, we're looking at, let's say, 300 seconds. But we want to be able to run the experiment up to 500 seconds.
For our experiments, or at least for the first ones, am I correct in assuming that we're testing sloshing in one axis at a time?
Yes. Yeah.
Okay.
The experiment design gets more complicated as the flight goes on, but yeah, we're doing one axis at a time initially. Yep.
All right. I'm not sure if this affects, because I know that we're having trouble at least with all of the data that our experiments are going to be collecting at once. When we're doing tests in one axis at a time, are we also going to be recording the motion sensor data in one axis at a time? Is that even a thing we can do?
Now, I'm sure it's possible to do it, but the motion sensor data that we're collecting, you can also think of it as part of the state of health data, right? That data is going to come to us anyway, and that's always recorded in three axes, X, Y, and Z. So maybe we can transmit less to the ground, but I think we need to get all three axes both recorded. The control mechanism and the BCT needs all three axes, and I would like to have all three axes to analyze when we get it to them.
Okay.
How many experiments do you want to run, and like exactly how long do you want our satellite to be in orbit?
That's a good question. Ideally, we're looking at this based on the last meeting with the UNP, some work I did over the Christmas break, combined with my thesis, indicated to get a nicely converged machine learning model, you need a large number of experiments, right? That's how machine learning works. The larger the training set, the better result you're going to get. So I used anywhere in my modeling, in my simulations, anywhere between like 9 models and 2,500 models as the training data set. But I found I got reasonable results in using what's known as a nonlinear autoregressive neural network with exogenous inputs. That's abbreviated NARX. The NARX models converged well if I got over 40 inputs for training. So as a minimum, what I'm recommending for the first set of experiments is 40 experiments on the satellite to get some reasonable data. Now, the total experiment package, if we look at more than just one axis at a time, if we look at various different control algorithms we want to upload and so forth, we could go as high as 250 to 300 experiments. But the minimum is 40. And so that's what I'm recommending.
See, thank you.
All right. Yeah, that question jumped ahead, but that was a good question. Something that I think we may need to explain, I think for if anyone that's listening is new, is we have a sister project going on, which is the 1G model, or the 0G flight. Would you like to explain a little bit about that and how it relates to the final /sat mission?
Sure. Hopefully you can see it behind me here.
Oh, let me pop this out and full screen it. Let's see. Yes. Or
Great.
There we go.
Excellent. Let me move this out of the way. Okay, so this is essentially the 1G, 1 degree of freedom experiment with the tank here and the reaction wheel here. You spin the reaction wheel and it imparts a torque moving the experiment the other way. You can imagine fluid being inside this tank to a certain level. And so when you impart a torque to the whole experiment and then you stop it, you have sloshing in this tank over here. So we're going to be replacing this tank with something that's more representative of what will be in flight, right? So this will be replaced with this one. Mm-hmm. And what we want to do with this experiment, there's a camera already mounted here. So we're going to be recording the data. There's an IMU, this red thing here. The IMU is an inertial measurement unit. It's accelerometers and gyroscopes. That's what's in here. We'll eventually line the inside of this tank with those pressure sensors. So we'll have essentially fully built a ground experiment to replicate what might fly in space someday. And this experiment you see right here will have a cage built around it, which will be built in such a way that it meets requirements to fly in a 0G flight, which is an airplane that kind of does parabolic arcs. And when you're on the down slope of that arc, you're weightless. So this experiment with a cage around it should fly in a 0G flight.
What would you say is the main purpose of this sister experiment?
I would say this is kind of has multiple purposes, but two of the main purposes are, one, to prove out the algorithms that were generated in the work I did for my master's thesis. Right, we're moving from equivalent mechanical models to an actual experiment, and can we mitigate the sloshing effect in 1G using this experiment, using the machine learning? So that's one reason for the experiment. The other one is to prove out our data collection algorithms of the camera, the pressure sensors, and the sensitivity of the IMU. And I guess the third would be to show the UNP that our ground/0G experiment is ready, and hopefully inspire them to drive us to the second round of funding.
So let's see. back. All right. All right. So let's see. So we've answered the question of the research, the benefits, and everything. Now let's see here. Suppose that the mission succeeds. What would we gain from it, and how would this inspire future missions?
Yeah, I think there's a number of benefits to be gained, but the primary one is to prove out the fact that if you're able to do both if you do accurate modeling on the ground, and we're able to prove that the ground modeling matches what we saw in space, then you can design using simulations for other spacecraft. You can design active control algorithms and train machine learning algorithms and various other types of software-based control algorithms to more effectively control the sloshing. And I'll give you a specific benefit. If you look at the James Webb Space Telescope, for very large slew maneuvers, when they want to point from one place to another very quickly, and if it's a long distance, they have to turn the spacecraft. That's called a slew maneuver. It could take 20 minutes for the propellant sloshing in JWST to settle down. So a practical benefit here is reducing that settling time so that you can begin observations quickly. And this also has applications for Earth pointing satellites as well. If you want to take pictures on the ground, you need a stable platform to do that. So the practical objective here is to reduce the sloshing settling time so you can start taking pictures much faster and conduct your observations or be pointed to a specific ground-based communications object faster. So that's sort of the practical benefit. And I would think that once those algorithms are proven out by our experiment, it's the type of work that commercial spacecraft builders would want to take into account in terms of when they build their own satellites on behalf of NASA or satellite companies. And then the last thing to consider is if we're able to control the satellite in software as well as the slosh baffles do in hardware, there's that much less weight in the spacecraft that can be replaced with experiments rather than baffles, which they're needed, but they're essentially dead weight, right?
Yep. Baffles are just pieces of mass. There is no real contribution once they've served their purpose. Or yeah. All right. So the next question is: we've gone through a few of the controllers, but for our mission, the machine learning algorithm is what we're developing. But I'm sure there's other controllers and control algorithms that we want to test. Can you give us a quick overview of all those algorithms and how they work, and I guess what their benefits, limitations, and other relevant details would be?
Yeah, I'd be glad to. That's a detailed question, probably requiring an entire paper on its own. But let me give you an overview. The first thing we're going to do is launch with the controller that exists in the attitude control system itself. Right. That's going to allow us to collect some critical data to train against, and not really risk using our own controller, which will be tested on the ground, but and we want to use the commercial grade available controller to start with to ensure we get some initial data. That's our minimum mission criteria. So that controller is a standard PID controller. We don't know a whole lot about it because it's proprietary to the manufacturer of the ADCS, but so we'll use that one initially.
Okay.
Next thing we want to do is beam up a different control algorithm that will make use of data coming in from the motion sensors, from the accelerometers and gyroscopes, and what's known as an output feedback or a time delay loop. So we will ask that controller that we beam up to it, we will say to it, use the last 20 values that you get from the gyroscopes and accelerometers to make a prediction on what the next 2 or 3 or 4 or 5 time steps would look like. That's the control window that you're looking at. And so we'll use this time delay controller, looking at past values to predict the future, to then compensate for the sloshing, right? We'll use that information to output a different control wheel acceleration profile in such a way that it should mitigate the sloshing. So it's known as a time delay or output feedback controller.
All right.
We talked about the machine learning controller. That's another one that we want to do similar with. We'll download the data from the initial experiments. We'll train it on the ground. We'll beam up that machine learning controller. And then we'll use that machine learning controller to try to mitigate the sloshing as well. Then we want to make use of the pressure sensor data. So this will be what's known as a reference governor controller. A reference governor controller is really just an add-on controller to any standard controller. So what that means is, let's say we'll use a standard PID controller to turn the satellite, but we want to put a constraint on what's happening inside the tank. And that constraint will be, in our case, on the amount of pressure detected by the pressure sensors inside the tank. So we will say, rotate the satellite using a standard controller unless you detect a pressure that exceeds a certain pressure threshold that we will preset, right? If you hit that pressure, maximum pressure threshold, then essentially what happens is it backs off the reaction wheel torque. It reduces the reaction wheel torque so that you stay under that maximum pressure impact. And once you have come under that threshold, it'll then bring the reaction wheel back up to where we wanted it. So that's a constraining type controller, and we're going to use pressure as the constraint. And then the last thing we want to do is tie all those together into one machine learning, output feedback, and reference governor controller, all in one large package. And so that's why I said earlier that our experiment gets more complicated the longer we're in flight, right? Because we start with a simple controller, and we start with a one-axis rotation, and we end with this fused controller and all three axes. That makes sense?
Yeah, it does. I guess, what would you say are the drawbacks of each of these controllers?
Well,
or drawbacks and benefits, I guess. So the benefits you've highlighted superbly well. So I guess now the question is, what are the limitations? Where does it go wrong?
Yeah, I mean, it's hard for me to comment on what the Blue Canyon technology drawback will be. I'm not sure what they have built into their proprietary work for slosh control, if anything. I would say the drawback of the machine learning controller is the fact that it is data heavy. You need a significant amount of data to get a really nicely trained machine learning controller. So the more data you put into it, the better answer you're going to get. I know that it works, and you don't just have to take that from me. The NARCS algorithms have been used to do many different types of applications in engineering and science. So we know that the NARCS machine learning algorithms work, but the drawback is you need data. I mean, you have to train the model for it to work. I think another sort of drawback of that method is that you train your machine learning model and then you input something that it has not seen before, right? So it should predict, and it does predict, but that new input has to be within the range of the areas that you trained. If you trained in this area, but you put in an input that was way, way out of where you trained, the NARCS model isn't going to predict that well. That's okay in our case, because the reaction wheel can only spin to a certain speed. So there's a natural limitation to what we can do anyway. So we'll train within that space, and the random input that we'll choose to predict against will be within the range that we trained. And reference governors, I'm not sure there's really limitations in terms of reference governors. They're relatively easy to to implement. So they're just used as a safety mechanism. In our case, we're not going to exceed a pressure that's going to blow the tank out or anything, but they are used. A good example of a reference governor can be making sure that the maximum RPMs of your engine do not exceed what the engine can handle. So reference governor controllers are employed in that case to restrain the amount of RPMs that the engine goes up to and doesn't hit the red line.
All right. Let's see. All right. The next question is, what do you consider are some failure points on the payload of our satellite? Or rather, what would compromise the research if something was to go wrong?
Obviously, the tank leaking would compromise the research. That would be a problem. The tank material, the fluid freezing would be a significant problem. The failure of the motion sensors, which I don't expect that to happen, but we need data. We absolutely need data for this to work. So I think having the right sensitivity and getting the data from the motion sensors, the accelerometers and gyroscopes, is kind of critical. And then getting some pressure sensor data is also important. We have to remember we have a transparent tank, and we don't have a full matrix around the whole inside of the tank, right? We only have certain places inside the tank that we're measuring pressure. So having some of that data is important. I think losing the video data would not be the end of the world. We would still be able to accomplish a lot of our tasks in terms of state vectors and uploading a new control algorithm if we didn't have the video data. But that's one of the things that makes our experiment unique. I guess you could look at it two ways. We'd still have a successful flight, but we would have lost one of our key measurement components. Does that answer your question?
Yes. So just to confirm, the video data it would compromise on the research, but it wouldn't necessarily end the mission if we just couldn't get a video down. It would be awful, but we would still be able to make do with the motion sensors and pressure sensor data.
That's right. Yes. Yep.
I'm gonna backtrack for a second. So before, when we were talking about the machine learning models, we mentioned that it's important to stay within the scope of what we use to train the model, right? So throughout our experiments, if we go for full mission success, we're gonna do a lot of different types of experiments. Does this mean we're gonna have to train different models if the experiments become like too drastically different from each other?
Yes. Yep.
Okay.
So we're not just going to train one machine learning algorithm. I mean, minimum mission success criteria is those first 40 experiments using the commercial grade controller, get that data to the ground, train, and send it back up. So that's minimum mission criteria. But throughout the rest of the experiment package, we're still going to be downloading that data. We will retrain the machine learning model every time, and then I don't know how often yet, but we will then beam up this revised machine learning algorithm to the satellite. So yeah, we are going to be constantly downloading and retraining throughout this mission.
Okay, thank you.
All right. Let's see. Okay, so something that we touched upon, I think, very shortly was there's a chance that we may induce unstable sloshing motion purely because of the control algorithm we're running. Maybe we haven't yet worked out the machine learning model. We did mention that it would dissipate naturally. I guess the question that comes from there is, what would we consider as an unstable behavior, or how would we characterize that? How would we tell apart the fact that it's unstable versus, oh, it's heading towards being stable?
Yeah, I don't know that I've thought a lot about that. So your question is, how do we know? We know what the endpoints are. We know we're going to control it, and we know that if it gets out of control, we can turn the control back over to the commercial grade and turn our controller off. So we know the two endpoints. But you ask a good question there. What is our threshold for saying we can't control it, turn it back over to go into safety mode in terms of the controller? It's a good question. I would think if we exceeded a certain angular rate, if we detected a torque beyond some kind of, I guess we could do it based on how close we're getting to the available control torque authority. We know what the control torque authority is of the ADCS. So I guess we could say it's a percentage. If we've hit a percentage of the let's say 80, 60, 75% of the control torque authority, then we should bail out and give it back to the safe mode controller. It's a good question. We should explore that one.
All right. Yeah. I asked because from the perspective of the mission designers, right, the current leads at the board and deputies, we would like to have within our flight software, a quantifiable, I guess, to be a little bit loose with the terminology, a massive if statement or an if condition where, okay, if this happens, we know to shut it off and go back into what we know works. Let's see.
I agree with you on that. So we'll have to do some thinking on it and figure out what that threshold is.
Sounds good. All right, let's see. I think we've answered almost all the questions so far. Spencer, Francesca, if you have any questions, now's a good time.
I mean, I hate to backtrack again, but I will. So, we mentioned earlier, when we were talking about failure points, that a big failure point for the tank would be if it were to leak, right? And I know that we've taken precautions to kind of prevent that. Can you catch me up to speed on what our current method is of getting the wires from the pressure sensors out of the tank?
Sure, yep. So if we imagine this is the tank, and this is the one that's going to fly here, but in space we will end up with these things being made of aluminum and not 3D printed plastic, right? They also need to be a little bit thicker. This needs to be a little bit wider here. This is too thin, so we're going to make it wider. And so what we intend on doing is essentially putting a hole inside here and screwing in what's known as a bulkhead connector, right? That is a airtight, watertight connector that'll go in here into threads that'll be in this aluminum. So then on the inside, we'll have some pins to solder the wires to. On the outside, we'll have a cable that will mate up to the plug that's in this connector. And this connector is called a bulkhead connector. It's specifically designed to take cabling or wiring from a pressurized to a non-pressurized space, or a watertight space to a space filled with water, right? That's what bulkhead connectors are designed to do. So that's a short answer to the question. It's a little bit more complicated than that, but that's essentially it.
Do you think bulkhead connectors still carry, like
some level of risk eventually, or are they like pretty like bulkhead connectors?
I'd be more concerned with, and this is what we should look into in more detail, is the fitment between the aluminum end and the actual tube itself, and making sure that that's sealed. That's where I'm more concerned about, not the bulkhead connector.
All right. Fran, did you have a question?
I do. I was hoping to wonder what you're gonna try and achieve by CDR.
So that's the January 2024 meeting, right?
That's
Yeah,
the
isn't-
October one.
It's flight selection review, right? I think CDR is in August.
Okay. I mean, ideally, we would have this completely built. We would have all three of the detection methods on here. You would have, I already have a control algorithm that works. It's just a very basic PID controller. So that's already integrated in here. I would want to have all of that up and running, have experiments run, know what the sloshing is in 1G, have videos processed in 1G. The videos, if you think about it in 1G, we're not going to have globules on the ground, but you have a tank level of water, and the tank, when it sloshes, it moves like this, right? So we should be able to detect the frequency of that sloshing and the amplitude of that sloshing. So having all of the experiments components on this, detecting imagery, frequency and amplitudes, as well as even training, using the experiment to train a machine learning model, same one I already used. I think those are achievable by that meeting, Francesca.
See, and what would you hope to what would you hope to achieve by flight selection review in January?
I would think we recently got approval to purchase a single reaction wheel from the ADCS company called Blue Canyon Technologies. I would love to have that wheel, that reaction wheel, on some flight software, replace this wheel here, replace this reaction wheel with the one from Blue Canyon, and show that we, in software, show that we can use the out-of-the-box controller, and that we can use our own external control software to run the Blue Canyon Technologies reaction wheel and conduct those same experiments over again. I think that would be a great thing to achieve for that meeting.
I agree with you. I think that will definitely prove that we can send our satellite up if we can achieve that.
And if we're doing that, which I just articulated, and we're building a flat sat at the same time, we're essentially proving a lot of both the payload and our ability to control the wheel, and that the satellite itself can live. We'll have the power, we'll have the solar panels, we'll have batteries and all that. So having both of those move in parallel, I think would be a great achievement for the group by that meeting.
Yeah, I agree.
So I mean, technically this podcast is also for people who might be watching in the future, so I feel like we should mention that this is taking place right after the preliminary design review. And I also want to ask, now that we've gotten like all of our feedback from preliminary design review from UNP, what do you think were the main takeaways from PDR?
So I haven't read it in detail yet, but I know what they told us from a payload perspective. They wanted to make sure that we had sufficient control authority. I was able to prove that out over the Christmas break. So I can go over that in some detail in another meeting. They were concerned about detection thresholds. I am also concerned about that. So now I know what the effect is going to be. That's another thing that I achieved over Christmas break. We're going to go back to them and to their experts with regard to the type of noisy data that you get from accelerometers in space, and see where I know what the effect is. Now let's talk about the sensors. They're going to help us with that. They were also concerned with the amount of data processing. We just started to examine whether we can run everything in the OBC or not. There were a handful of other points that, one of the other main points was they thought our experiment plan was a little aggressive. So I scaled that back considerably. That's why I threw out that number 40 as opposed to like 252. So at 40, I'm gonna have a tough time compromising further. So those are some of the feedback that they gave us during the meeting, and I've addressed all the points that I can remember from the meeting.
Okay. And then what do you think are going to be the biggest challenges in between us right now and critical design review?
Unfortunately, one of them is administrative, and that's procurement. But if we put that aside, I'd like to think we have university support to kind of power through that one. I think time might be one of the obstacles in our way. Again, not an engineering obstacle, but we have to put the time into it to get it done. Software is rearing its head in the payload group now. I think that we're going to be, at least in payload, we're going to be a little challenged. We have somebody working on the camera now. It's a third person, unfortunately, but we need to control the camera not with the Windows application, but with C software. So hopefully that new student will achieve that. We're going to have that reaction wheel in a number of weeks. We're going to need to learn how to write software to control that reaction wheel. So that's a concern. And then for the ground anyway, I think we discovered some good solutions in the last 2 weeks on how to use the ground-based pressure sensors. We're going to be using MATLAB, but we're going to need to find a programmer that can pull raw pressure sensor data off of the communications interface, probably SPI, and get that to the ground. So and get that into the OBC to control against it. So I think software is going to be one of our primary concerns going forward.
So I guess this is we're already at 1, so I guess only a few more questions, if any. A question that I'm going to ask you, which would hopefully help people in the future as well. What, within the payload subsystem, what would you say are the major, I guess, aspects, and how many people do you want, or how many people would you want working on each thing? You obviously mentioned the software is one of them. What else is there that you would like us to, that you would need in order to get your stuff done?
I need 100 people.
Well, I can't promise that many, but I could try.
I'm a big believer in putting two people or so on a given project. I think they inspire each other, and it also allows you to check each other's work. So 100's a little high, but 1 is low. So I'll bracket it with that. So can you ask the first part of that question again?
So I guess the first part is, within everything that needs to go into making the payload, what would you say are like the main aspects? Like, so one of them is, writing the pressure sensor control code, one's the camera. Like, what would you say are all the aspects, and how many people would you like working on each one?
Yeah, I mean, so that's relatively easy to answer because we have very specific experiment sections, right? Pressure sensors is one of them. So we need programming written against the pressure sensor communication interface. We need software written against the camera. We need software written against the ADCS data. And really, that's just a matter of collecting the data, right? Putting that into getting all that data in one place so we can control against it. Another component is the ADCS itself, right? We have to learn how to write software to turn on the ADCS, to spin it up to a certain angular velocity, and change its orientation by 30, 60, 90, 180 degrees, right? We need to write software for the ADCS. We need to write ground fusion software. That's another component that I mentioned earlier. So that's a 5th component. And then I guess the last component is, once we have figured out what our controller is, we have to beam that up to the satellite and use the sensor data as inputs to our control algorithm to initiate our new controller. So I think that's a 6th area that we need to focus on. And those are divided into flight software and ground software components.
What would you call the last area, I guess? And
I would call that the active control of the satellite in flight software. That's the last area.
active control of SAT plus flight software. All right.
Yep.
Let's see. Okay. I think exactly what it sounds like. But yeah, actually, I guess this will be a bit of the preview into the next episode, which won't feature you. It'll just be me and Spencer. But I think I'm going to be taking on the ADCS control role following the summer and onwards. So hopefully I can definitely help you out with that. Let's see. Are there any other questions or comments, concerns for the podcast for Mike?
I thought it went really well.
Yeah, I'd say this went really well. All right, well, thank you for joining us, Mike. It was a really good podcast. It actually went way better than I thought it would. I expected a lot of errors, at least on the recording side and whatnot, but we'll figure that out.
I'm glad to do it, and hopefully it's beneficial for those that'll listen in the future.
Yep. All right.
I took a lot of notes. If you guys like want to take a look on the document, just letting you guys know. I tried.
Oh yeah, in the document we have notes being written on everything. So, if there's someone out there who, in addition to listening in or watching this video, wants to read the documentation, or not the documentation, the notes that we took, it's all here. Well, the vast majority, at least. I think there's like a few that we answered like in between other questions, but besides that, I think this first episode is done. I'd say we did good. All right. Thank you guys for joining.
Thank you.
All right.